It's the most interesting thing there is. In other words, I am the most interesting thing in the universe. But thank you for having me. It's a great pleasure to be here. As my friend Chris Field often says, to understand ourselves is to understand the universe. And in that understanding, you should be able to destroy the divide between physiology, psychology, biology, philosophy. All of these disciplines are just different perspectives on the same thing, namely how we are part of a self-organizing system. So the challenge then becomes to identify the principles that underwrite self-organization, and that includes self in the sense of me and you, to understand how we are organized. So the free energy principle, I think, can be thought of as an endeavor to describe the principles or the methods by which you might want to simulate or describe the kind of thing that you and I are in terms of a self-organizing but sentient kind of thing, particle, person, or creature. Um, so my expertise is not really in comparative anatomy or evolutionary anatomy, but certainly my understanding of the functional anatomy of the brain would in part be consistent with that model, in the sense that there are certainly differences between different species and indeed different kinds of things, living things. Um, that could be understood in terms of displaying or exhibiting different kinds of behavior. So technically, in my world, you would be trying to understand the function of a brain in terms of its role as a generative model or a world model that is apt for engaging with, making sense of, and navigating a particular eco niche, which means that the brain of a virus would look very, very different from the brain of a human being, simply because they occupy different niches at different scales. And things like the free energy principle, but also principles or ideas from early cybernetics, such as the good regulator theorem, tell you that a brain, and indeed any internal machinations of anything that controls or has a controlled interaction with its niche or environment, must be a model of that particular niche. So that means, depending upon the niche in the world, whether it's inside a cell if you're a virus, or inside a village if you're a human being, then you'd expect there to be fundamental differences in the dynamics and the structure of the brain. So I don't think it's a silly idea to draw a bright line between different parts of the brain in terms of the cerebellum and the cerebral cortex, or the limbic system, in the sense that one can associate different parts of the brain with different aspects of an implicit generative model. So one really important difference, one would imagine, is the ability of things like you and me to be able to plan. And if we are able to plan, then we must have a generative model of the consequences of our action. And that generative model must be instantiated, must be embodied in the functional anatomy of our brains. So I would expect to see a different kind of anatomy in you and me, because we can plan, compared to a small insect that was not able to look into the future or generate predictions about the consequences of doing this or doing that. So on that view, you could also argue the very fact we have very large and expressive bodies and a very complicated physiology. Then we'd also have, in order to control, not in terms of propositional thoughts, but in terms of, say, autonomic reflexes and the like, then we would also need to have a generative model of our own bodies, and our own bodies in different kinds of states. And many people argue that that kind of interoceptive ability underpins emotions and possibly a minimal form of selfhood. So I would imagine that the limbic system, for example, would be an expression of the necessity of having a generative or world model in the neuroanatomy that was appropriate for making sense of and controlling a more elaborate kind of body. So on that view, then that hypothesis, I think, is actually quite consistent with current understanding of functional anatomy. That there are different kinds of things. Those different kinds of things embody their world models or generative models in their brains, or if they don't have a brain, in the intracellular kinetics and dynamics and possibly functional genomics of a very small living creature, such as a bacterium or a single-celled organism. But as you get to more multicellular organisms and you get things with brains, then you would have, I think, a spectrum of different kinds of brains, depending upon the scale and the nature of the environment that that thing exists in. I think it has been in, well, let me first of all saying that that kind of cartography and cytoarchitectonics is very, very important in understanding functional anatomy. And it speaks to one of two principles of brain organization, namely functional segregation, the anatomical or spatial segregation of a specialization for a particular function. And that usually goes hand in hand with the anatomy at a microscopic or mesoscopic scale, as described by Brodmann's cytoarchitectonic areas. So that was the basis of much of the early advances in brain imaging, trying to understand functional segregation in the human brain. So, for example, there are specialized regions in the occipital part of the brain that are specialized, say, visual motion or color processing. So for the first time, in fact, one was able to confirm the hypotheses, largely based upon lesion deficit models and neuropsychology, that in turn were related or understood in terms of purely anatomical studies. Neuroimaging was able to confirm the hypothesis that indeed the brain showed this kind of modularity of functional segregation, where particular parts of the brain were important for updating beliefs or processing different attributes of the sensorium. And we've already discussed some. It could be about my body, it could be about my visual input, or the causes of my visual input. So that work has been advanced progressively over the centuries and over the past decades, with equipping that kind of anatomical characterization with different attributes, such as the receptors that characterize different parts of the brain, so the cerebral cortex, and also a greater and more refined anatomy, not of the local structure, but of the connectivity. So I'm thinking here of myeloarchitectonics and tracing studies that have now also been endowed with another sort of aspect, which is in terms of the function and the predominant cell types, using things like optogenetics. So there's a vast research program bringing these different ways of characterizing not just the anatomy, but also now the physiology and the connectivity as assessed by tracing studies and ways of imaging white matter tracts in the brain, connections between different brain areas, which have all spoken to a better understanding of the structure of the brain. And that's important because we were just rehearsing the idea that the anatomy and the structure of the brain is an important instantiation of the brain as a generative model of the lived world. And of course, as a model, it is now telling you a lot about the environment that this brain has to make sense of and to act upon. The second principle, so I mentioned functional segregation as the first principle that was evidenced by this kind of cytoarchitectonics and the cartography that you got from brain imaging. The other principle is functional integration. It's the coordination of these different regions, an understanding of the distributed neural processing or the message passing that can be thought of in terms of the influence of this brain area on this brain area, and how that message passing can be understood in terms of using your world models to make sense of sensory data, but also, I repeat, how to act upon the world. And there are lots of advances in that space. My favorite advance is an understanding of functional architectures or functional anatomy in terms of heterarchies or hierarchies. And that's been an important insight in terms of one structural aspect of our brains and our generative models, that they have a deep structure, a hierarchical depth, very much like you would find multiple hidden layers in deep learning and machine learning and artificial intelligence research. That's that hierarchical depth, but also a breadth in terms of the factorization that is apparent in the physiology and in the anatomy and in the cytoarchitectonics and the myeloarchitectonics. So these are really important insights into the wiring and the structure and the physiology and the dynamics on that structure that tell you more and more about the brain as an organ of perception and action. The indeterminacy you're talking about would be under the assumption that you have a linear or subsumption hierarchy where you can just order all the cortical areas, say Brodmann's areas or functionally identified areas, in a serial hierarchy. I don't think that's necessarily the best way to think about things. So what people generally think about nowadays is a heterarchy, where you can have a hierarchical-like arrangement, but it's not strictly ordered. So this non-uniqueness, I think, is slightly misleading. There may be a completely unique heterarchy, which is a more relaxed kind of sparse coupling that has a hierarchical aspect, but it's not a strict linear hierarchy. And in many senses, it would be very surprising if there wasn't a unique heterarchy for a particular species, because then you wouldn't be able to define that species as having characteristics in terms of their world models. So I suspect that the game really is this identifying what is the unique heterarchy, and that heterarchy would have to accommodate things like cortico-subcortical relationships, which are very distinct from just moving up hierarchical levels in, say, the visual cortex. And of course, once you get into the prefrontal cortex, you have very clear evidence that things like, for example, the frontal eye fields do not fit comfortably within a linear hierarchy. So now you've got a much richer picture of heterarchical organization, and it's just a question now of understanding that aspect, that global macroscopic aspect of the heterarchy, in terms of, well, what kind of generative model would entail this sparse connectivity structure and the contextualization of one level in a hierarchy on the children of, or say, a lower level in a linear hierarchy. I think an important concept here, well, an important issue here is the distinction between forward and backward connections that define a hierarchy. So if you think about it, you can't define a hierarchy unless you can define what is an ascending connection and what is a descending connection. So I think the more important and unique aspect of connectivity that we deal with is this dissociation between forward and backwards, the asymmetries in different kinds of connections. And as soon as you have that distinction between forward and backwards, you can now start to think about what does that mean for the influence of this area on that area. You know, is the other area my child or my parent? And if the connections from me to this other area are of a backward sort, a top-down sort, then that means this region is my child. And if it's my child, then I am now providing contextual guidance, coordination, inductive biases from a Bayesian point of view, or the point of view of, say, Helmholtzian unconscious inferences perception. I will be providing top-down priors for this. Conversely, if my connections to you are of a forward sort, I will be informing you. I will be sending, for example, under predictive coding schemes, information conveyed in the form of prediction errors to change you so that you provide me with better guidance. There are certainly modern interpretations of Freudian free energy and bound free energy. And my friend Robin Carhart-Harris is one of the key authors, but also there's a scholar called Mark Soames who has he's probably one of the world's experts on the writings of Freud, but also deeply invested and very knowledgeable, not just about the neuropsychology as it speaks to, say, things like psychoanalysis, but also the neurobiology of hierarchical message passing, predictive, hierarchical predictive coding and processing in the brain. So a simple answer would be that the modern day implementations, both in computers and in simulations of biomimetic or brain-like processing of Helmholtz's idea about unconscious inference, will be understood in terms of predictive coding. And exactly as you've just said, that means that in order to perceive some sensory impression, I have to have a representation or an expectation about the hidden or latent causes of those sensory impressions. Say, for example, I might have the hypothesis that I'm looking at a face. And if my hypothesis is correct, then I would predict I will be seeing these things using my eyes. And furthermore, if my hypothesis was that I was in conversation, I would also expect to hear certain things. So I can predict what I would see and what I would hear. And then I can use those predictions to test the adequacy of my hypothesis by comparing the predictions with what I'm actually sensing, and that's just the prediction error. And then that prediction error then can be used to update my hypotheses deeper at higher levels in my cortical or subcortical heterarchies. And that can be understood from many perspectives in predictive processing. Mathematically, it's can be called Bayesian belief updating, that I'm using my prediction errors to update my beliefs in order to explain away the prediction errors. So if I predict perfectly my sensory input, then the prediction error is 0, and there is no more drive to change my mind, to update my beliefs, or change my neural activity that is encoding that particular perceptual synthesis or explanation. So that's a very simple description of predictive coding in, we'll use the word hierarchies, although most people still are happy using hierarchy, but, because of what we talked about in terms of no unique hierarchy. So in this hierarchical formulation of belief updating under a generative model, that people would refer to as predictive coding, you've got this notion that the forward connections, the ascending connections, are conveying prediction errors, and the descending backward connections are conveying the predictions. And this recurrent cycling enables you to build an explanation for your sensed world that explains away the prediction errors. Now, that explaining away can, in some sense, be linked to Freudian notions of free energy. If one makes the simple association between free energy and the overall amount of prediction error. So by explaining away, I can really bind that free energy or that prediction error, because I'm removing it by accommodating it. And I use that very, very simple analogy because it is also consistent with the technical use of free energy and the free energy principle, which is not quite a Freudian free energy. It inherits more from the work of Richard Feynman in terms of a probabilistic description of the goodness of fit of my explanations for what is going on. So you can think of variational free energy and the free energy principle as a more general way of talking about prediction errors. So or more generally than prediction errors is surprise, or the implausibility of these sensory data given my beliefs or hypotheses about how these data were caused. So this hierarchical predictive coding story simply means that I'm always trying to minimize my surprise by changing my mind to find a better explanation, which means I'm trying to minimize my free energy, which has the look and feel of a Freudian kind of free energy, but you'd have to now associate, well, which prediction errors, because these prediction errors live at every level of the hierarchy. So I can have very low level sensory prediction errors. I could have prediction errors in my limbic system. I could have prediction errors very deep, high in the hierarchy. And as such, everything is trying to minimize prediction errors everywhere. So there's going to be a yin yang between how much precision I afford certain prediction errors relative to other prediction errors in finding that balance. When it comes to modern day formulations of this Freudian notion, people sort of turn to, again, the anatomy to try and get a handle on the neurobiological implementation of a Freudian concept, and usually associate certain components of the brain with various aspects of self. And one very popular notion nowadays is the regions that constitute the default mode network, quite simply because this set of regions has been implicated on many lines of evidence in terms of perspective taking, introspection, the kind of processing that could only be instantiated or associated with something that has a notion of selfhood, in the sense that to have a perspective, I have to be something that has a perspective. So that's where most of the literature that I know about tries to get a handle on the relationship between higher levels, say default mode, constituent areas of the default mode, in relation to more peripheral regions that are closer to the sensory input. And then one has to ask, well, what about the amygdala and the limbic system? And I'm sure we could talk for a long time about that in terms of Freudian ideas. that's a very good question, which brings a lot of themes to the discussion. Let me first of all deal with that important asymmetry between forward and backward connections. So it is generally thought that forward connections are more driving and linear in their nature, whereas backward connections are more modulatory and nonlinear in their nature. And this holds in terms of simple visual hierarchies from V1 to V2, from V2 to V4, but also if you think about forward connections from subcortical thalamic systems through forward to cortical systems. So where does that come from? Well, under predictive coding schemes, it has a very simple explanation, or in fact, two explanations. The first explanation is a reflection of the fact that we live in a nonlinear world. So we have occlusion, for example, so that what we see is not a linear mixture of its causes, which means that when we predict or generate a prediction of what we would see, we have to have those nonlinearities as part of our generative model, as part of our world model. And as we have just discussed, this has to be physically instantiated in the anatomy. So that would mean that the top-down predictive mechanisms that are generating predictions of the sensory input have to include this kind of nonlinearity that is inherent in the world that we're trying to explain. So that's one principal reason why the top-down connections are nonlinear and modulatory, whereas the bottom-up connections are not. The bottom-up connections are there under a predictive coding narrative, simply to drive high-level representations to a better explanation, and that driving is quite linear. It doesn't have to be it doesn't have to be non-linear, and indeed mathematically it is not. It's a linear drive. However, there's a second important aspect to the effect of top-down connections or descending connections that have a modulatory aspect that I suspect you'll want to come back to at the end of our conversation, which is the prediction not of the content of what you're seeing, but of its quality in terms of how much confidence, how reliable are these, say, prediction errors. So if I'm in the dark, literally, if I've got my eyes closed, or somebody reduces the light intensity, the ambient light intensity, then the visual prediction errors have much less information. They're very imprecise. And I have to know that because I now need to selectively ignore the prediction errors generated from this very imprecise sensory source when it comes to allowing them to update my beliefs. So I also have to predict the precision. And in predicting the precision, I now modulate or revise the gain or the excitability of neuronal populations encoding prediction error. So this second order effect, which is not about predicting the content of sensations, but the context in which those sensations have been generated, namely their reliability or their precision, also entails a top-down modulatory aspect. So that's very important. And I've forgotten the other two bits of your... Can you remind me what the last two parts of your question were?
So how does it relate to perception and action and music, for instance, as well?
Right. Yeah. So that extending this predictive processing or predictive coding account into the realm of action is a very important move. Sometimes articulated in terms of enactivism, sometimes in terms of things like perceptual control theory, sometimes in terms of things like active sensing. We call this active inference. And what that says is, it's not just a question of understanding how sensory impressions update our Bayesian beliefs about the world, which may or may not be personal or narrative or propositional beliefs, but just the implicit probabilistic beliefs that the brain holds in virtue of responding or having this population activity or neural firing. That's not sufficient because you are in charge of the data that you sample. So just by moving our eyes around, we can choose what visual impressions to sample in order to do the best kind of updating to resolve our uncertainty about what's causing all my sensations, what is literally out there beyond my skull, beyond my sensory epithelia. So that means you have to understand action in the context of perception. So action is in charge of the sensations that underwrite perception. But of course, you need perception in order to decide how to act next to get the best kind of sensations in order to do the right kind of perception. So there's a circular causality implicit in this extension of predictive coding in what I would call active inference. And the interesting thing is, it's the same quantity that is driving both action and perception. And you can think of this as minimizing prediction error. So you can think of two ways of minimizing prediction error. You can either change your mind, literally by being receptive, certain parts of the brain being updated in terms of sending prediction errors, changing your neuronal representations, changing your mind so the top-down predictions now eliminate or destroy those prediction errors. So that will be perception. Or you can now act upon the world to make the sensations more like the predictions. And that will have the same effect because you're just eliminating the prediction errors, you're destroying the prediction errors, not by changing the predictions, but by sampling the world in a different way to make your sensations that have been actively solicited more like the predictions. So this casts action and perception in the service, the joint service of both trying to minimize prediction errors, the difference between what I predict and what I actually sense. And that means that you can look at action as fulfilling predictions. So we're always predicting what am I likely to see next and how will I act to make that prediction come true. So always predicting a slightly optimistic future that is characteristic of the kind of thing that we are. And then we use all our reflexes, both autonomic and motor reflexes in terms of moving our muscles or secreting things in order to realize a future that is characteristic, a short-term future that is characteristic of the kind of thing we are. What about music? Well, there are a number of different ways in which you can understand the allure of music. Certainly from also an inactive perspective, because at first glance, you might think listening to music is a very passive thing. It doesn't involve any action. That's a nonsense. To attend to actively listen, to hear, to to listen as opposed to just hear, is, I think, underwrites the perception and processing of music. So to choose to act means you have to understand now what is the appeal of music. And there are a number of people who think the appeal of music is the opportunity to resolve uncertainty or surprise or expected prediction error, that it's sufficiently predictable but predictably unpredictable. So you have to keep on listening to see what the musician is going to do at the end of this riff or this 8 bars. So this is like a second order predictability. It's predictably unpredictable, and therefore provides the opportunity to reduce prediction errors and minimize free energy. You may be asking, well, how does that fit in with inactivism and our motor actions? There is a sort of side story here that much of that predictability rests upon covert action while we're listening to music, being in the groove and without actually moving or singing out loud, we are actually dancing inside to this music in order to, if you like, furnish the best, most temporary, precise predictions of the tempo and the cadence afforded by listening to music. Well, there are a number of ways to understand the free energy principle as a way of describing this kind of predictive processing of an inactive sort, because you can think about free energy as effectively the amount of prediction error. So I give you a couple of very mathematical answers to that that may satisfy people who've done physics and statistics, but will mean nothing to people who haven't done physics and statistics. But if they have, then strictly speaking, a prediction error is a free energy gradient. So when I write down a statistical model, a probabilistic model of some data, say of the kind of model that you might use in a statistics package to test your hypotheses with some experimental variables with an analysis of variance. That's the kind of model I have in mind. The prediction error here is the residual. If I now write down the mathematics of, or certainly a generic Bayesian formulation of this kind of statistical modeling, it turns out that the residuals, under certain assumptions, Gaussian assumptions about the nature of the random effects, the prediction errors are just the free energy gradients. So if I now think of the job of estimating the best explanation for my data, say, when performing a t-test, for example, or fitting out an ANOVA model, what I can do is I can adjust the parameters of my model, the coefficients, say, of a linear regression, in order to minimize the free energy. And when the free energy has been minimized, the gradients are zero. So this is what I meant by destroying or eliminating or explaining away prediction error, because the prediction error is just the gradient of the free energy. So in minimizing the residual sum of squares or the prediction error associated with all the data or all the sensory modalities, that can be expressed as minimizing the free energy. And then you can write down the dynamics that require that as a gradient flow. And it turns out that that gradient flow on this quantity that drives the flows, the dynamics, say, for example, neuronal dynamics, is exactly the kind of gradient flow you will see in anything that self-organizes. And that's where you get to the physics part of the free energy principle. And what basically that says is that there is a background story to this Bayesian interpretation of neuronal dynamics in terms of fitting a generative model or an observation model or a forward model or a world model to sensory data, that emerges from just a consideration of systems that are separable from the environment in which is supplying, say, data. And to make it very, very simple, the way you write this down is you assume that any entity, any thing, any particle or person has an attracting set of characteristic states that characterize the kind of thing they are. So it'll look as if they're always gravitating, or their dynamics are always gravitating towards this attracting set. And then you work out what's the implicit function that drives these gradients, these gradient flows, and that function turns out to be the variational free energy we've been talking about. It is just effectively under Gaussian assumptions, the sum squared errors or sum squared residuals, or the sum squared prediction errors under Gaussian assumptions. The generalization of this notion in terms, you can generalize it in a number of ways. You can generalize it in, in terms of Bayesian or approximate Bayesian inference using the variational techniques introduced by Richard Feynman that we mentioned earlier, to understand this in terms of the thermodynamic homologues of this free energy. And as you pointed out, the reason it's called a free energy is it can be decomposed into an energy, an expected energy minus an entropy. And that's important because it gives you a different interpretation of this fundamental gradient flow that must be characteristic of anything, in the sense that you can always describe self-organizing systems as effectively minimizing their surprise or minimizing their free energy or minimizing their prediction errors, equivalently maximizing the negative surprise, which is interestingly model evidence. So some people call this self-evidencing. And the evidence here is just the probability of my sensory data given the kind of thing I am, as defined by my generative model of how those data were caused. So that's a sort of philosophical take on this surprise minimizing. It's exactly the same as gathering evidence from my model of the world. Hence the resolution of uncertainty and always trying to realize things in the future that are characteristic of you, or certainly the way you understand your world. But to come back to this thermodynamic or physics perspective, what that means is to self-evidence, to resolve surprise or minimize surprise, to be curious, to respond to epistemic affordances, just is to minimize the expected energy, which is effectively the accuracy with which you can predict your sensory input, whilst at the same time maximizing the entropy of your beliefs. So that's quite crucial. What does that mean? Well, it means that you're keeping your options open. You're not committing to very specific beliefs that you would need to explain these data extremely accurately, because then you're overfitting the data. So this maximum entropy aspect is very important from the point of view of things like Occam's principle, from the point of view of I repeat, not committing to a particular very precise belief, a very low entropy belief. It's also very important to understand this in relation to James's maximum entropy principle. So as a physicist and a mathematician, you would look at the free energy principle as dual to a constrained maximum entropy principle. So again, if you now look at physics as the science of measurement, and measurement is basically building probabilistic beliefs about the state of something that you are measuring, then what James was able to show is that all of physics can be described as basically keeping your options open in terms of maximizing the entropy of your measurement under constraints, and those constraints are exactly the accuracy constraints that are afforded by your generative model. So there's a number of sort of interesting and sometimes counterintuitive aspects to free energy minimization. That you're trying to maximize the entropy, the uncertainty associated with your beliefs to keep your options open, while at the same time trying to provide a very accurate account. So it's very much like Einstein's maxim, keep everything as simple as possible, but no simpler. And that sort of balance is afforded by the balance between the accuracy and the complexity, or the energy and the entropy. And then that's just a statement of Bayes optimality. Well, adaptive behavior is this literally increasing adaptive fitness through learning. Adaptive fitness just is the model evidence. So it's just a free energy minimizing process. So adaptation and active learning is just an expression of free energy minimization at a slower time scale than belief updating, because here now you're talking about the parameters of your generative model. If you are in machine learning, this would be the connection weights. If you're a neurobiologist, this would be the connectivity, the effective connectivity, synaptic efficacy. So if you write down the free energy minimizing processes for any plausible generative model and look at the specific dynamics associated with the parameters of a generative model, which are usually, I say, associated with connection strengths, then you get for free what emerges is associative plasticity or Hebbian plasticity with associated terms, but also decay terms. So again, come back to this sort of yin-yang between accurately accumulating evidence, but also forgetting in an optimal way stuff that is redundant or too complicated. So there is no mystery here. Adaptation just is a free energy minimizing process. You mentioned selection previously. So in my world, the take on evolution through the lens of theoretical biology is that evolution rests upon natural selection, and natural selection just is Bayesian model selection, and Bayesian model selection is selecting those models, those phenotypes that have the greatest marginal likelihood or evidence. That is just the adaptive fitness that measures the fit of this phenotype to this environment. So the model evidence just is a measure of the fit of your generative model to the environment that is being modeled, and therefore you can talk about maximizing adaptive fitness or adapting to your environment or your context or this new situation as you can articulate that or just write that down as maximizing your model evidence or minimizing your the path integral of your free energy. It's all the same thing mathematically. So you mentioned reinforcement learning and reward learning. You can certainly subsume reward learning, and if you mean by reinforcement learning, you mean that kind of adaptive learning or associative plasticity that is driven by a reward, that is reinforced by a particular reward. You can certainly subsume reinforcement learning within active inference and the free energy principle, but that kind of adaptation or learning, is a very special case. You don't need, most of our physiology and most of our behavior and most of our choices do not depend upon sparse rewards. For example, your homeostasis does not depend upon reward. A thermostat doesn't need to be rewarded in order to do its job. So the vast majority of adaptive behavior is just minimizing prediction errors, where for say a thermostat, the set point is provided by top-down predictions. So there's no notion of reward there. But you can have rewards in the sense that they epitomize or describe characteristic outcomes of plans or policies. So if you move now to the slightly more complicated domain of creatures that can plan into the future. So now we're not just talking about minimizing prediction errors, we're now talking about how many prediction errors would I minimize if I did this in the future as opposed to that. Then you can write down now priors over the outcomes that this kind of thing would expect to encounter, and then you can work out the probability of encountering those outcomes if you chose this policy or that policy. So you can explain reinforcement learning as a special case of adaptive learning or learning generally under the free energy principle, but it's only part of the story. There are other more important parts, which is expected information gain. So I'll just. I'm not sure how long we've got. I feel as though we've been talking for a long time, but these are really important points. So in the moment, in minimizing prediction error in a merely reflexive way of the kind that you would require to understand homeostasis, for example, you're just minimizing free energy or prediction error, or you're maximizing the likelihood of the current data. When it comes to planning, when it comes to behavior of the kind you'd associate with an agent like you and me, as opposed to a thermostat or a virus, then the game gets much more interesting, because now we also have to represent what we are doing and what we are going to do. And that means your generative model has to have a model of the consequences of action. And then you have to work out, well, what kind of policies would I commit to? And it turns out from the physics, the path integral formulation that we were talking about before due to Richard Feynman, it turns out that the most likely policies, the paths into the future that we will infer ourselves following, have two components that speak to the dual aspects of Bayes optimality. And these two aspects can be expressed in terms of optimal Bayesian decision theory, and on the other hand, optimal Bayesian design theory. So the first rests upon minimizing some expected loss function, so negative reward, if you like, whilst the second rests upon maximizing expected information gain. So when I said that the reward is just a small part of it, what I meant was it's the expected information gain which usually dominates most of our behavior. Certainly now, you are engaging in resolving uncertainty about, what am I going to say next? You're not chasing money or expecting fruit drops at the end of this. You're doing it because because it's got you're responding to its epistemic affordances. You're responding to the expected information gain by actively listening to what I am saying. You're resolving uncertainty. There's no reward here. So the reward part sort of kicks in terms of supplying constraints on our responses to our epistemic foraging, to maximizing the way we sample the world or attend to the world in a way that resolves our uncertainty. And then you can write down very precise constraints that I expect to be I expect this kind of outcome of the kind you'd find in economic games or reinforcement learning paradigms. That's an excellent question. I'm not quite sure what the modular paradigm is, but it could be exactly the same as the Markov blanket paradigm. So in answer to the last question, it's not the case of how does free energy minimization lead to an autopoietic formation of a boundary around myself, for example. It's the other way around. So the free energy principle says that if something exists, it can always be described as looking as if it is minimizing its free energy, or if you're a philosopher, self-evidencing. So then you have to ask, well, what is something? What is an entity? And if you think about that carefully, then you will arrive at the notion of the Markov blanket. So what you are effectively saying is, if something exists, it will be describable as minimizing its variational free energy. But for something to exist, it has to have a Markov blanket. So what all you're saying really is that things stipulatively defined as possessing a Markov blanket or a boundary that individuates them from everything else, that separates the internal states of something from the external states. So, for example, the sensorium or sensory epithelia and all the active states. If there is a set of boundary states that intervene between my internal states and external states, then I exist in the sense that I can be separated from my environment. I have characteristic states that are not those of the environment. That means that I can always be described as self-evidencing or minimizing variation free energy, and you can tell a Bayesian probabilistic predictive processing like account, and this would be the Bayesian mechanics that inherits simply from having a Markov blanket. So how does that relate to modularity? I suspect, I don't know, and you probably know better than I do, but I suspect there's quite a close connection, because there are a number of ways of thinking about the Markov blanket. You can think about it in terms of the conditional independences from the point of view of dynamical systems theory, which is the way that I think about things from the perspective of a physicist, trying to understand causal coupling and the characteristics of interesting systems cast in terms of random dynamical systems. But you could also think of it in terms of, say, just simple systems theory. So the Markov blanket is just the collection of inputs and outputs from a given system. So if you just look at sort of standard systems theory, You just draw boxes around one system, and then you link them with inputs and outputs. Now, the Markov blanket just is a specification of the fact that there are separate boxes, and the active states of the Markov blanket, the influence of the inside on the outside, is just the output. And the sensory states, which is just a description of how the outside influences the inside, is just the inputs. So a Markov blanket is just a generic mathematical probabilistic description of the way that any given thing or system is coupled to another thing or system. And in the absence of that specification, you can't distinguish between the thing and everything else or nothing. So you can't talk about anything. So you have to have a Markov blanket before you can talk about anything. You, me, your cells, the institution in which you study, anything that exists as a natural kind has to possess a separability or an identifiability in characteristic states that are distinct from the environment in which you find it. So we can answer that question quite easily because we've done all the hard work in setting up hierarchies and heterarchies and the modulatory effect of the top down being in part playing the role of predicting the precision. So the answer to that is there are many ways of understanding altered states of consciousness, and I just bring you back to that because that's very interesting from the point of view of neuropsychiatry. So you could actually look at many conditions in mental health and illness as evincing certain altered states of consciousness that can be read as false inference. So, for example, and I mean false inference in a very technical and simple sense of type 1 and type 2 errors, inferring something there when it's not, and inferring something is not there when it is. And of course, that's a perfect description of things like hallucinations, inferring that something is there when it's not there, or disabling conditions like dissociative syndromes and neglect syndromes, inferring something is not there when it actually is there. So that's important, I think, to say out loud, because that means that you can now understand the Bayesian mechanics of inference in relation to altered states of inference and altered states of mind and perception. And if we now know the anatomical and physiological substrate of that Bayesian mechanics in a brain, we can now understand that the effect of changing those substrates on the ensuing belief updating and the ensuing inference processes, and also what that might look like in terms of false inference or altered inference. Say, for example, the very definition of psychedelics is that you have abnormal visual impressions or interpretations of your visual data. How might that happen? Well, if we just go back to this deep generative model that has this hierarchical structure, say in the visual system, a relatively simple hierarchy. We were talking before under the predictive coding view of message passing or belief updating of a hierarchical sort in the visual system. You've got prediction errors at every level, all driving their parents to provide better explanations so that they are explained away. And that speaks to now a competition between eliminating prediction errors. So which prediction errors are you now going to weigh or afford a greater potency in driving the beliefs in order to eliminate themselves? And this is where the precision comes in. So if you think that this prediction error is very, very precise, is very reliable, it's you have great confidence that it's conveying newsworthy information that I had not previously predicted, you're going to assign it via modulatory mechanisms more precision. And it's now going to predominate in terms of your belief updating. And that can occur at any level in the hierarchy. So if I wanted to attend to the sensorium, I would assign more precision, more weight, physiologically more synaptic gain to the prediction errors very close to the visual input, and I would attend to the elemental features, the colors, the edges of my sensory input. On the other hand, if I was in the dark, I would, or had impaired vision, for example, I may afford more precision to deepen the hierarchy. So I'd start to see faces where there weren't faces, because that's the best explanation for something that's something like a pareidolia, of seeing faces in clouds, for example, when you can't, when it's dusk and you can't quite see the cloud. So this speaks to getting the balance of precision right at different levels of the hierarchy is a really key mechanism for perceptual synthesis. If you're a psychologist, this would just be basically the balance between endogenous and exogenous attention, attending to the outside by weighing or increasing the precision at the sensory level of heterarchies or hierarchies, as opposed to investing high levels of precision deep in your constructed world that provides those empirical priors or inductive biases for lower sense making. So the physiological mechanisms of this, exactly as you were asking or talking about before, just rest upon neuromodulatory effects. How are they mediated in the brain? By particular neurotransmitter systems that activate receptors that don't cause a discharge of the cell, but alter the conductance of the cell to evince these modulatory like effects. And so the key neurotransmitter systems are exactly those implicated in altered states of consciousness and in psychiatry and its pharmacological remediation. All the monoamine neurotransmitters, things like dopamine, serotonin, acetylcholine, noradrenaline, oxytocin. Well, yeah, there's a whole list of those. Things like psilocybin activate 5-HT2A receptors, the partial agonists on the 5-HT2A receptor, that is thought to affect, through a cascade of little mechanisms intrinsic to certain cortical areas. It's basically thought to relax the priors by effectively undoing a disinhibition, so effectively reducing the excitability at these deep levels in the hierarchy, or certain levels in the hierarchy, so that you can pharmacologically induce a different kind of attentional set, enabling the release of, or if you like, attention to more elemental structures that are now unconstrained by prior constraints. So now you can start to see faces in houses and houses in faces, simply because you've now flattened that landscape of prior precision and prior constraints, because you've effectively switched off or relaxed the constraints higher in the generative model. And sometimes that can be very useful and therapeutic in terms of getting yourself out of a rut, as it were, either perceptually or behaviorally. So in brief, that's one version of the rebus hypothesis that links the landscape of belief updating to the pharmacological effect of certain neurotransmitters and attention on message passing in the brain that's doing the belief updating, which is moving around this belief landscape. That's a very difficult question to answer, but it's a very interesting question. Yeah, when you talk about words like improvement, as a physicist or a theoretical biologist, that has no meaning. What's better, a virus or me? Could I improve by becoming a virus, or could the virus improve because what exists and it exists in an ecosystem. So do ecosystems change? Yes, they do. Does that mean you're losing certain constituents, denizens of that ecosystem through evolutionary processes? Yes, absolutely. Is our ecosystem changing? Yes, it is, absolutely. Is it changing in a way which say, for example, speaks to the emergence of artificial intelligence. I would suspect it's not changing quite that quickly. I think we've had this kind of thing, this, if you like, it's changing, and it's changing quite slowly, and it will change in a way in which people will adapt to it. So now children are now much more fluent with social media and living their lives online, and literally, their ability to use their thumbs in terms of being able to manipulate little tiny keyboards is beyond me. I mean, I'm of an age where I've never used these technologies. So literally their musculature and their cerebellum are wired differently simply because the ecosystem is changing subtly. But it's been changing for a long time. Since the introduction of an abacus and then iPhones, this. I'm thinking here of sort of Andy Clark's extended mind notion that we are certainly being able to download a lot of our cognition onto technology. We're certainly changing the ecosystem in terms of globalization and the availability of information. That introduces lots of pressures and difficulties for people. I generally see it as a bad thing. I think social media is a bad thing because it does disrupt those Markov blankets. But people will adapt to it, and they'll reform their Markov blankets and attend to or disattend to the right sources of information. But they will have to adapt. And in that sense, the answer to your question is, that there is an evolutionary advantage and disadvantage. And I think probably best stated in terms of second order selection or meta selection. So the question is not how will we change or be changed by any advances in technology, say artificial intelligence or globalization or the like. I think it's the rate of change which is the important thing. So I'm always taken back to perhaps Stuart Kaufman's notions of second order selection, but even before that, the idea that the one expression of the law of requisite variety, but now in an evolutionary setting, that you need to explore the space of hypotheses, the space of generative models, the space of phenotypes in order to optimize it for this particular eco niche, requires the generation, the exploration of that. So there's continual movement. Technically you could liken this to a certain kind of Red Queen dynamics. You've got to keep on moving to stay still, to stay in the game. That is written into it. I think the question is how quickly. And there are empirical studies and theoretical analyses that say that there is an optimal rate of change. So, for example, if you take fruit flies, Drosophila, and you allow them to reproduce in an environment with a constant temperature, their mutation rate falls. But if you now put them in an environment where the temperature changes from generation to generation, so it's a volatile environment, then their mutation rate increases. So I think from the perspective of is change or mutation rate both of the environment and the creatures and the phenotypes within that environment, could it be improved or not? I think that the question should be posed at the rate of change, and certainly that's very relevant from the point of view of climate change, but possibly also in terms of technology and artificial intelligence. At the moment, there can be a mismatch between the volatility of the environment and the capacity of the members of that ecosystem to adapt to that change. That could be disadvantageous, but on the other hand, it could be very advantageous. You're just weeding out those people who can't adapt.